Let's take a look at hot water unit heaters that would be used either in residential or commercial applications. So I want to identify some of the performance characteristics that would affect output for a unit heater, hot water unit heater that would be identified. So what we're typically dealing with here with these types of heaters would be something like, I'm going to just draw a picture here. What typically happens with most of these systems here is we're going to run, we'd have a unit heater. On that unit heater, there's going to be a prop fan. You got your little motor. You got a coil that's going to have connections, hot water supply, hot water return as an example, and you might be going in and out of there, and hopefully you have some heat extracted. Most of these are prop fan type applications where we're going to supply the cool air from the room into here, and we'll leave here with the nice warm air. So pretty basic hydronic system. Commercially, you see them all over the place. So when we make adjustments to our control systems that are going to affect the performance of this, let's look at how they're rated. Let's look at exactly, how are they rating these systems. So the first thing we're going to hit up on here is in this table 11 that I have here, it says to determine the heating capacity of a unit heater at any water temp and entering air temp, multiply the capacity at 200 degree entering water temp and 60 degree entering air temp from this table. So right there, we've just identified specifically that our hot water unit heaters that are used in our commercial and residential type systems actually are rated based on an entering water temperature of 200 degrees and entering air temp of 60 degrees. And anything outside of that, we're going to need to apply certain correction factors. Now, you'd be amazed at how much of a correction factor that will end up being. The other thing that I want to point out is that we're typically dealing with, in most of these applications, we're normally going to deal with a 20 degree temperature drop in and out. So that means that if the typical application is going to give me 200 degree supply water temp, that means coming out of here, there's a pretty good chance that I should be around 180 degrees Fahrenheit, provided that I'm getting the output or performance on that. Again, 60 degree Fahrenheit entering air temp, and the output will be dependent on how many B2s that I get out of there. So let's take a look at this. So in the rating system that they're identifying here, we're going to identify an entering water temp in my diagram of 200 degrees Fahrenheit. Okay, and I'm going to go all the way over until I find a factor of 1.0. Now, if I go straight up on that 1.0, I'm going to be able to identify that the entering air temperature that it was rated at was 60 degrees entering air, and the boiler water was 200 degrees. And this is going to be corrected from the nominal values that the manufacturers provide as the heating outputs on these systems. So let's take a look at a couple of these rating systems that we have here. So I'm going to pull this one up here. Now this is a typical performance data. This one here happens to be from a Modine unit heater. I apologize for the darkness of this. And again, you'll notice that up on top here that they've got 200 degrees, 60 degree entering air, 20 degree water temp drop is their standard method of rating these. Now, if I take a look at a very typical application that we might have. So maybe I've got an application where I happen to have an HS63, this particular heater. Now that HS63 is going to have a nominal capacity of 47,000. Now you might be wondering, why is it not 63,000? Why on the earth would they do that? Well, unit heaters are rated, the same unit heaters oftentimes are used to handle both steam as well as hot water. And the steam units are utilizing latent energy by the conversion of the vaporous steam into liquid condensate, and you're going to get more BTUs out of those units. When you run water into these systems, you're going to get much less capacity out of those, which is going to be, you're taking 200-degree water in, you're extracting 20 degrees of sensible heat out of that water at the desired flow rate, and then of course that gives you those BTUs. So the GPM that you would need in order to achieve that would be about 4.7 gallons a minute. The water side pressure drop would be a roughly 0.8 feet of water or feet of head. And of course, if I continue further, there'll be some other data that would be identified here that you may or may not be interested in. Specifically the airflow. One of the things about unit heaters is the airflow is a constant. Because of the prop fan, there's no variable speed fans that we typically use. So in this case, 1120 CFM of air is what we would typically expect out of there, which of course, what they also identify for us is the final air temp, and this would be what would leave that unit heater. So remember, we have 60 coming into that heater that it's rated for. We would have a 98 degree temp leaving that. So if a person wanted to have a little bit warmer air coming out of that heater, they would have to slow that fan down. But of course it will affect the performance. It will give you less capacity when you slow that fan speed down. You could very easily put a speed controller on there to do that. So, and they're also giving me motor horse as well as RPM roughly on there. So that's a little bit on the performance data, the nominal value that they have. Now if I pull up another one of these, an HS108, the HS108 has a capacity of 81,000 BTUs. It would need to have 8.1 gallons a minute with a pressure drop of 3.2 feet of water. That would be in and out of the hydronic side of that particular unit. And of course, if I look further and further, you'll see a lot of very similar data. 2010 CFM, a lot of airflow, a prop fan, and of course 96 degrees is the leaving temperature on there. Again, that may feel cool when it's blowing on people, but these are units that typically are not put in applications that would need to have real critical, control. So they're going to be expected that there's going to be air moving around and that it may feel a little bit cool. But there again, that's the typical application. So what I want to do is just go through a really quick performance demonstration on this thing. And on an HS, we can use the HS108 as an example. So on the HS108, we had, of course, 81,000 BTUs per hour. So we're going to remember that. And of course, if I were to apply these correction factors on that, and let's say that I wanted to only supply 50 degree air, or 50 degree water, 150 degree water, and I'll slide all the way across here, and you'll notice that even if I kept the 60 degree air as entering, and I maintain that as my minimum space temp, I would have a factor of 0.643. So that would put me at the 81,000 BTUs per hour as the capacity times the 0.643 as the rating factor, and this, whatever this number happens to be, will give me the BTUs per hour that I would expect to get out of this particular unit. So that's a couple of little things. So what if you get a customer that decides, you know what, I want to run glycol, or I want to run a certain type of a glycol. Well, the performance factor of glycols also would have some impact on that. And this is true of all systems. So if I happen to have, let's say, 40% ethylene glycol in my system, you'll notice that even at the, let's say, in an average temperature of 200 degrees, which would be on the higher end of that, there would be roughly about a 9% decrease in capacity due to having the glycol. It's a little bit of a factor, not major that we would have to deal with it, but we do need to understand that that is going to have a detrimental performance factor on that particular unit as well. All right. Additionally, I want to show you one other factor that we're going to be dealing with, and there we go. So there's another curve that they can also identify in some of these. So one of them, I can use the HS108 as an example. This one's actually showing me as more of a graphical curve that identifies water flow rate as well as water temp rates and to some extent. So let's say that an HS108, we can use that as the example on there. So what we're going to do is identify that as the nominal rating system at a 20 degree delta T is right up here. And that right there is going to tell us that it's about 81,000 BTUs per hour as the rating system. And our GPM is approximately, 8.1 GPM based on this particular chart. And of course, what if I have, less water flow? Of course, if I have less water flow, then I will end up I'll have a bigger water side delta T, but the resulting factor, because of that average water temp being lower inside the unit, we're going to get less BTUs out of that unit as well. So there's a couple of ways to kind of determine it, but there again, it's more to recognize the importance of water performance. And if I change temperatures in a system due to my boiler, what does that do for me? What impact will it have? And will my customer be able to get that same amount of energy out of that as possible? The one thing that I'll use an example here, and I'd like to just go through a real quick example on this, is that if I happen to have a customer who's got this, let's say, HS108 water heat emitter or a unit heater, and let's say they have this in their shop, and in their shop that's blowing around. As we remember seeing from the from in our shop, we recognize that there's a lot of wrong way here. Let's go back. There we go. So what we recognize in that HS108 is it's nominally rated for 81,000 at 8.1 gallons a minute, and it's going to blow 2,010 CFM of air. Now, here's the thing to remember. At a 200 degree supply water temp, you're going to get 96 degree air coming out of that unit heater, assuming you had 60 degrees going into that. Now, that's a 36 degree rise. All right, now 96 degree air blowing around in a space may make that feel somewhat a little bit on the cool side. Now, what is the impact of us changing that water temp? So if we change that water temp, and let's say that I either lower the water flow or the average water temperature in that unit heater goes down substantially, my output is going to drop considerably. So I might be having, instead of 81,000 output, maybe I'm dealing with, if I cut the water flow significantly, maybe I'm dealing with now only 50,000 BTUs out. I'm still blowing around the same amount of air. That's going to make that customer feel somewhat cool. So most people, when they install a unit like that, they're going to try to install it in a manner that would not be blowing directly on people. And they're going to try to get it so that they recognize the significance, and the reason for lowering this water temp down is going to be to save energy on the boiler side of things. It also does a nice job also of sufficiently making additional run time on some of these systems. There again, on systems, if you don't have good airflow control, you might have some issues with that on there. So that's a little bit on performance ratings of some of these. So just to recap a couple of things here. So if we were to look at the heat emitter output and what would happen if I increase my supply water temp, I think all of us could see, well, if I increase the supply water temp, gee whiz, I get more output. I get a higher and an increase in output. If I were to decrease the airflow across this unit heater, well, then I wouldn't be pulling, we're talking about this fan. If I were to slow that fan down, I actually would get less BTUs. It wouldn't be able to take as much of the heat output between the 200 and the 180. So you're going to get if I were to decrease airflow, I would lower my output. If I were to increase airflow, I would essentially increase my output to a point. If I were to increase the GPM, there would be really nothing detrimental about increasing the gallons a minute. In fact, if we were to look at this one sheet that we had earlier, and I was describing to you, if I were to lower the water flow on here, in every situation we saw a decrease in capacity. Vice versa, if I increase the GPM, I will see an increase in capacity, again, to a point. There'll be a point where you won't be able to get much different on there. Let's take a look as another summary here of what is the impact on if I were to take my entering air temperature and I were to increase the air temperature coming into that system. Well, I think that's best looked at in this particular sheet. And in this case, if I were to say, you know what, I don't want to have 60-degree air, I want to maintain my shop at 70-degree air. So at 70 degrees entering air temp, you'll notice that you would lose roughly at the 200-degree entering and 60 from that to the 70, you would have lost roughly about 9%, about 8 to 9% of the capacity. And again, as long as you have the capacity, it's not going to be a problem. If you are shy in it already, that might be an issue on there. So that's something to consider. And then if I were to decrease the air temperature, I would end up getting even more capacity out of a system with the same water temp. And as you can tell, I would increase it, just a decrease from 60 to 50, I would have seen a change from 1.0 to a 1.08. So it would have actually seen an increase in capacity of roughly about 8.4%. So the point in showing you this is that you understand the impacts of air temp, the impacts of water temps, of average water temps in coils, as well as airflow, and whether it's plus or minus, and how to read the rating systems on these. Now, this was just one example for a Modine unit heater system, but these same principles can be applied on any type of a heating system, any type of air or fan coil type system.